Today's notes are about the Bohr's model. Before we can get into Bohr's model, we need to learn a few things about waves and light in itself. So waves have several parts to them. First, you have what's called the wavelength. It is the length of one complete wave. This symbol is sort of like an upside down Y. Frequency is the number of waves that pass a point during a certain time period. So for instance, if you mark somewhere on the road and you counted how many cars passed within 1 second, which isn't going to be that many based on cars, that would be frequency. How frequently you go to a store, you count how many times you go in a certain time period. So frequency is for waves just like it is for anything else. The units for frequency are in hertz, which is the same thing as per second. Then we have amplitude. It is the distance from the origin to the trough or the crest. In just a second, I'm going to show you what a trough and crest is. We're not actually going to do any calculations with this, but if you do take Chem 2 or any upper level science, you will have to do calculations. Take a second, pause the video, and label your wave like this. Okay. As you can see, the A's stand for amplitude, which is the origin, which is this line here, the middle of the wave, to the crest, or it's from the origin to the trough. Crest is pointing to the highest point of the wave. Trough is pointing to the lowest point of the wave. Wavelength, which is this, is from any point of the wave to the exact same point of the wave, is a wavelength. All visible light travels at 3.0 times 10 to the 8th meters per second. So no matter what color you're looking at, it's traveling at the same speed. A lot of people have the misconception that red moves fastest or purple or whatever, but they're all traveling at the same. What is different is the wavelength and the frequency. Wavelength and frequency are inversely related. We've talked about this word before, inverse, meaning they do the opposite. So red is extremely long compared to violet. So since the wavelength is extremely long, it is going to have a low frequency because hardly any waves pass through a certain amount of time. Whereas violet, if you call this time, right here, it has a lot more waves passing through that segment than red. So they are inverse. Long means low. Short means high. So L and L and sh. Okay, long, low, short, high. Then there's frequency and energy. Frequency and energy are directly related. This means they do the same thing. So this should make sense because think about the heartbeat or if you have one of those radios that has shows you the frequency of the music and things like that. Typically, when you have a lot of waves, you have a lot of energy. So same thing. The higher the frequency, the higher the energy. Think about when a heart monitor flatlines. It flatlines meaning there's no waves going through, so therefore no energy. Less waves, less energy. Light. Particles of light are called photons. Einstein is the first one to come up with the idea that light has properties of both waves and particles. This is called the wave-particle duality. So again, photon, key vocabulary word here, is a particle of light that carries a quantum of energy. So it's sort of like a ball of energy, but it has properties of waves. Quanta just means the smallest quantity of radiant energy. Then we come to Bohr's model. Now remember, he's Bohr ring. He has the rings on his atom where the electrons exist. They are called energy levels. So he said electrons exist only in orbits with specific amounts of energy called energy levels. Therefore, electrons can only gain or lose certain amounts of energy. So if you're sitting on energy level 1, you're only going to be able to go up a certain amount of levels or go down. So your energy is based on that. So therefore, only certain photons are produced. And this is where we're getting light from electrons jumping up and down inside the atom. So the energy of a photon depends on the difference in energy levels. Okay, so first off, you need to know two vocabulary words: ground state and excited state. Ground state is the lowest possible energy of an electron. The question in your notes asks about what happens when an electron absorbs energy. This picture is showing you exactly what happens. So the energy that's being absorbed is called a photon. So in this first picture, the energy is going towards the electron, it's being absorbed. The answer to your question is the next picture. So what's happening from the electron from here to here? It's going from the first energy level and jumping up to the second energy level. So the key thing that you've got to know is that when an electron absorbs energy, it moves to a higher energy level. So just like you, if you were to drink an energy drink, what happens to your energy? You go up. You might even start jumping like the electrons do. You go from your low energy state, which is ground state, you drink that energy drink or whatever gives you energy, and you jump up to a higher energy level. The electrons are the same way. Now, when it jumps up to this higher energy level, this is called excited state. So, excited state is when an electron temporarily occupies an energy state greater than its ground state. So the question here is asking you what happens once the energy goes away, or what causes the electron to go back down. So when you have the electron in excited state, it's got to get back down to ground state somehow. So to get back down to ground state, it has to lose that energy. When it loses energy, when it goes from high to low, it loses energy. It's got to go somewhere. It's released in the form of a photon. So the key thing you've got to know here is when it goes from high to low, it produces a photon, which is why we see light. So the only reason we're seeing light is because the electrons are jumping from high to low inside their atoms. So this is constantly happening when electricity is flowing through the atom. Okay, you now need to pause the video and get out your reference table. On the very back of your reference table, you should see the diagram that looks like this. Very back page. So you should see a model that looks like this. This is Bohr's model of the hydrogen atom, and at the very bottom you should see a spectrum. What you now got to do is I'm going to tell you some information. You've got to be able to tell me some numbers that go with it. So for instance, what is the wavelength of an electron going from n equals 5 to n equals 2? So you have a diagram here that has a bunch of circles. Here you should see n equals 6 all the way to n equals 1. The n represents energy level. So this question is asking, what's the wavelength produced when it goes from n equals 5 to n equals 2? So what you're going to do is you're going to first find where it does n equals 5. So you're going to, n equals 5 is right here. And you're trying to find the electron that goes from n equals 5 to n equals 2. So then n equals 2 is here. You need to find the electron that goes from 5 to 2. These little dots are the electrons. So you need to find the one that starts at this red line and has an arrow pointing to this one. So if you go here, you should see this one starts at 5 and it ends up at 2. So if you follow that down, it gives you your answer, which is 434. Now, this has a unit. If you look at the very top, which I don't have it up here, you should see that it says measurement in nanometers. This means you're going to put in M. So 434 nanometers. Okay, Based on that information, you should now also be able to tell me what color light is being produced, because depending on the wavelength and the frequency, you should be able to tell me that. Now, the biggest problem going from this to this part of the spectrum is this is in nanometers, this is in meters. So the first thing you need to do is take this number, so 434, and you're going to multiply it by 10 to the negative 9th. This is how you go from nanometers to meters. When you do this, you should get 4.34 times 10 to the negative 7th. And all you have to do at that point is compare it to this line number. It's just a line number. You're trying to figure out where 4.34 falls. So is 4.34 fall between 7 and 6.5? No. 6.5 and 5.9? No. So you keep on going until you get to blue. Blue is from 4.9 to 4.2. Does this number fall into there? Yes. Therefore, your answer is blue. Again, it's just a line number. Compare it to where it falls. Now, Bohr came up with this idea that this should work for every single element. So he did studies and tests and experiments and things like that. Now, he did figure out that each element does have a unique bright line emission spectrum. They produce a specific light based on the element that it is. This is called the atomic fingerprint. But his calculations that he did were wrong. It only worked for hydrogen. Therefore, scientists had to rethink his model and came up with the idea of electron clouds instead of the rings.